Going on. All right. Let me get a drink real quick. Just testing the mic real quick. All right. So today I'll be reading File System, finishing this book. Then I got an OA to do, so I'm going to do some LEET study. Then I'm probably gonna work on some Gleam depths, the Gleam depths issue. Then I'm probably gonna do the OA. Then probably gonna cook. Then I'm probably going to do Plant Engine. So like this week I have, there's approximately no upper bound to the amount of work I have to do this week. So stop messing around. We're going to discuss issues related to mass storage systems. Choices in designing a file system and its implementation on disk. Side note, just want to tell you what's up. Before you get too far into this, I just want to talk about some books I'm looking forward to reading. Especially during Christmas break, where I don't have these other like artificial deadlines. Um, here. So I'm thinking, so for my birthday, I'm gonna get this book, Compile Optimizations for Scalable Parallel Systems. I was actually looking at like compiler books, and this one's actually from a professor from Georgia Tech, which is kind of dope. So definitely read that. Um, so this is what we're finishing right now. This I'll finish. This I'm not reading. Haskell Programming First Principles finish. Logical Foundations probably not finished. That might be a next semester project. Um, Static Program Analysis. I kind of want to finish that. Yeah, I'm gonna finish that as well. Christmas break. This I'll finish. This is like my nighttime book right now. Category 3 for programmers. Maybe. Let me see that actually. Category 3 for programmers. Haskell and Scala. I definitely prefer the Haskell one. Maybe I'll read this next year. Yeah, that's pretty interesting. I kind of want to read that. But that's 600 pages with dense content. It would take me around 20 to 30 hours. Maybe more. Probably more. Maybe 40 hours. Um, Theory of computation. I think this one's kind of early-ish. Theory of computation. Then again, I don't recognize that cover. Not sure why that's on there. This I'm definitely reading over Christmas break. Linux kernel development. I'm like slowly reading that. I'll finish that. I'm gonna finish up on it. This I might not actually read that one. But yeah. All right. I don't even know why I brought that up, but let's do it. Why is it called a Manila file? Unless it's from the Philippines. Right. They're made from Manoa hemp. So it's a treat, like going through your folders and such. Ellen creates a alias. An inode is a data structure for the representation of a file. Get access rights with Chmod. Chone. Right, W, you're on. Name, you get the name of the file. Alias, other names that exist for the same file. Owner, who created the file, oftentimes. Time when the file is first created, creation time, last write time, read, write, and X privileges. Size. Some commands touch, make dir, rm dir, ln-s. That is for making a new symbolically equivalent name. ln, making a physically equivalent name. Chmod, chone, group, copy, move, cat, more, less. Design choices in implementing a file system. So you have 4 components to the latency for doing input-output from to a disk. Seek time, rotational latency, transfer time, DMA transfer. Tired or not? Getting a Dutch oven for Christmas. It's kind of hype. Alright. So the figures of merit, which means criterion for judging its performance, are fast sequential access, fast random access, ability to grow the file, easy allocation of storage, and efficiency of space util. So we're going to look at some allocation schemes and discuss the data structures needed and the impact of the scheme on the figures of merit. Some common terminology for the rest of the discussion. An address is a triple index of cylinder, or perhaps like a three-dimensional index, cylinder, surface, and sector. File system views the disk as consisting of disk blocks, physically contiguous regions of memory. The smallest granularity of disk space managed by the system is a disk block. For simplicity, we'll use the 4-tuple sil, surf, sec size of disk block corresponding to a particular disk block and designated by a unique integer. So baz, just to empty nothing, I guess, is small. Text file medium, JPEG large. The disk allocation scheme has similarities to both the fixed and variable size partition-based memory allocation schemes discussed in Chapter 8. At file creation time, the file system pre-allocates a fixed amount of space to the file. The amount of space allocated depends on the type of the file. The amount of space allocated to the maximum size of the file can grow up to. Figure 11.4 shows the data structures needed for the scheme. Each entry in the directory data structure contains a mapping of the file name to the disk block address and the number of blocks allocated to this file. The file system maintains a free list of available disk blocks. Makes sense. So this is much like memory allocators. So you got first fit or best fit, combine nodes on delete. Sometimes you do compaction to combine nodes. Yeah, it's like variable size memory partitions. External fragmentation. Since you have a fixed size chunk of disk blocks, you have internal fragmentation as well. So they're stored on the disk itself because it has to be persistent, but it is cached into memory. So allocation can be expensive depending on the algorithm used, first or best. Since it occupies a fixed partition, both sequential and random is efficient. When positioning the disk head at the starting disk block address for a particular file, the scheme incurs very little additional time for seeking different parts of the file. So it is hard to increase the size of a file once it already exists, because so that makes sense. Contiguous allocation with overflow area. Now you have an overflow legion that allows spillover of large files that do not flow into this fixed partition. Okay, so we got a slightly different variant. Now we got linked allocation. So we deal with allocation at the level of individual disk blocks. So you have a free list of all the disk blocks. File occupies as many disk blocks as it takes. Allocates disk blocks from the free list as the file grows. Free list may be a linked list of the disk blocks, with each block pointing to the next free block. The head is cached in memory. Expensive traversal times. You can also do it as a bit vector. That's kind of smart. The free list changes over time as applications produce and delete the files. So it's not going to be contiguous. On the plus side, allocation is quick since you can do it blocks at a time. Easy growth. No external fragmentation. Never requires disk compaction. File access, kind of trash, especially for random. Error prone. File allocation table. It's a variation of linked. So you have a table on the disk that contains a linked list of the files currently populating the disk. The scheme divides the disk logically into partitions. Each partition has a FAT, in which each entry corresponds to a disk block. Free busy field indicates the availability of the block. The next field gives the next disk block of the linked list that represents a file. The next field. So in the file allocation table, you have the file, what is that, file allocation table? You have free and busy bits, then you have the next bit. The next is the next, okay. It's the next disk block of the linked list that represents the next part of the file. Yeah, and then -1 is the last for the file. So I don't think this is right. The next field gives the next disk block of the linked list that represents a file. I feel like that sentence is just straight up false. It's not the next one that represents a file, it's the next one that is. It's the block containing the next contents of your file. It's not just that it represents a file in general type. A distinguished value -1 indicates this entry is the last disk block for that file. A single directory for the entire partition contains a file name to FAT index mapping. Okay. File name to FAT index. Wow. No, that's kind of clean. Foo takes 30 and 70. So you just jump around. Let's try to analyze the pros and cons of the scheme without reading it. So a pro is that sequential read time. It's kind of goated. Random read time is okay. You could end up like if you're randomly reading at the back. So like on average, you're going to be reading in the middle, I imagine. But you might load the whole thing at once. I don't think you really load individual blocks, do you? So I'd say sequential is good. Random is okay. Growth, good. What's the other metric? Growth. Growth. Compaction. On delete, you're gonna have more work to do because you gotta clear the table and do the bits. Okay, let's see what they say. Since FAT captures, so there's less errors. efficient allocation times, similar to linked lists for, okay. Yeah, that makes sense. Yeah. Similar to linked lists for sequential, because they're still just bouncing to each next one, but better for random because you know which ones. Why is it better for random? Because even in the linked list, you're going to go through all of them and then on the average be in the middle. Needs the next block pointers. Huh. So one of the biggest downsides is the logical partitioning. For the end user, that's not pleasant. Artificial scarcity of space. Due to its simplicity, it was popular in MS-DOS and IBM OS too. Okay, so now we're moving to indexed allocation. Indexed disk block for each file. The indexed block for a file is the fixed size data structure that contains the address for disk blocks that are part of that file. This aggregates data block pointers for a file scattered over the FAT structure into one table per file. Table is called an index node or an inode and occupies a disk block. The directory contains the file name to index node mapping. The scheme maintains a free list as a bit vector of disk blocks. So why is this better than the previous one? Well, because the access time to the nth block within a file is constant. So the random access time is quite good. Sequential access time is quite good. The error time, I don't understand the error thing. Just don't write errors. Just don't write errors, bro. So it's better for random access since it's in one data structure. Limitation of the maximum size. Okay. The inode is a fixed size. I imagine you can software around that. Since inode is a fixed size data structure per file with direct pointers to data blocks. So yeah. Number of data blocks. So what is a Linux max file size? 2 terabytes. I mean, I don't even have 2 terabytes of disks, so I think I'm chilling. What other schemes that remove this restriction on a maximum file size? Okay. So I need to just shut up and start reading. So skip the example. There's a bug in here, bro. Scheiße, уберите себя. Убери себя. So fixes the limitation by making the inode an indirection table. I don't know what that is, bro. So let's look up indirection table. Now we're just gonna keep reading. Makes the inode for a file an indirection table. With one level of indirection, each inode entry points to a first level table, which in turn points to the data blocks. So it's just multi-dimensional tables. The inode for foo contains pointers to a first level indirection index blocks. Dude, contains pointers to a first level indirection index blocks. Why are there so many errors in this book, bro? Yeah, this is accessible. Whatever, dude. How is this like revision 15 of the chapter and you just never read this sentence? I'm actually perplexed. The inode for true contains pointers to the number of first level indirection tables equals the number of pointers that an inode can hold. These first level indirection tables hold pointers to the data blocks of the file. Forty, 100, 201. So you're kind of, the inode represents these intermediate tables that just allow you to have more indices. The downside is that even small files that may fit into a few data blocks have to go through extra levels of indirection. Yeah, I don't really care to have a file that's that huge, honestly. I guess it depends on how big these data blocks are and how big the tables are to whether, like, imagine this book. I don't know. Then you have hybrid indexed allocation. So what was this? Multi-level indexed allocation. So hybrid, so you can do both. You can do direct pointers, but if it's too big, you do indirect. All right, perfect. You create a file, only the inode is allocated. File size does not exceed the amount of space. Dope. So let's compare these strategies. Contiguous. So yeah, this was complex free list, messy file growth, medium allocation overhead, all types of fragmentation. With overflow, you have a continuous block, but you can write anything, your extra stuff, to like a dedicated overflow buffer. Good for small files. Still both fragmentations. The linked list strategy, non-contiguous, you have a bit vector, so it's good, dependent on seek time. Random access is trash. File growth is very good. Allocation overhead, small to medium. Space efficiency, excellent. With fat, you get these non-contiguous blocks, and a file is like a table jumping between them. Good, but dependent on seek time. Very good. File growth, true. Small allocation overhead, large space efficiency. Good space efficiency. With just the OG indexed, non-contiguous blocks with the bit vector, seek time, limited growth. And then multi-level index is where you can do these like indirection tables. Just have as many nested tables as you want. Then hybrid combines indexed and multi-level indexed to allow you to have small files that are not like taking up all these tables for no reason, but also larger files that need the extra, that exceed the amount of blocks that the length of the I table is. And so you need indirection tables, and so they are made. For the integrity of the file system across power failures, persistent data structures of the file system have to reside on the disk. So you cache them. Putting it all together, so the Unix operating system uses a hybrid allocation approach with hierarchical naming. So the directory structure is no longer centralized. Each inode represents a part of the multi-part hierarchical name. Leaf nodes are data files, intermediates are directory. Inodes have a type attribute. You also have a ref count. So let's see it. You get the inode, you got users, type directory, file name, and inode address. Inode for users. And for users, inode address. Are these? Huh? I mean, I understand the concept. Complete inode structure for users, fac, Rama, foo. Okay. So, you got something else, you got an example. Some examples. Remove temp bar foo, the contents of the inodes. Temp bar foo. This will be removed. That was easy. The file bar was deleted. Which bar? This bar? This bar. This is temp bar gag. So bar's a folder, bro. Touch creates a 0-byte file. rm temp bar foo. Temp slash bar slash foo. Oh, yeah, we just did that. So the ref count isn't accesses, it's the amount of tables. If you have like these different users, it's not the amount of tables that it's in. So symbolic links require some care. So talking about more about inodes. Every file has a UUID called an inode number. It's an index into a table that has all its information. And the metadata is long. Occupies an entire disk block. Collection of inodes that forms a logical table, and the inode number is simply the unique disk block address that indexes into this logical table and contains the information about the file. All the inodes occupy spatially adjacent disk blocks. So that's the maximum number of the files. Components of the file system. So you call the FS manager. So you have the media independent layer. That's the UI provided to users. Name resolver, where you can close, open files, read them. Name resolver. Media specific storage space allocation layer. Device driver. Media specific request scheduling layer. Distinct instance of the bottom two layers. Excuse me. The user program uses APIs to open, close files. You also resolve names. Space allocation module does the free list. Device driver actually interacts with the hardware, and the disk scheduling algorithm determines which requests from the user program, or perhaps the operating system, We're going to be serviced in what order? The anatomy of creating and writing files. Your program makes an I/O call to create a file on the hard disk. Following steps chase the path. API routine for creating a file. Am I dumb right now? No, I'm tweaked. The API routine for creating a file calls, validates. Am I tweaking or is the book tweaking? The API routine for creating a file calls, validates. Dude, why is this? The API routine for creating a file call, no S. Creating a file call, probably. Validates the call. So you'd likely. By checking the permissions, access rights, and other related information for the call. After such validation, it calls the name resolve. The name resolver contacts the storage and allocation module to allocate an inode for the new file. Okay. Storage allocation module gets a disk block from the free list and returns it to the name resolver. Storage allocation module will fill in the inode commensurate. Bro took vocab 9, but grammar 2, bro. The storage allocation module will fill in the inode commensurate with the allocation scheme. Okay. Let us assume the allocation in effect is the hybrid scheme. This file is being created without any data yet. Without any data as yet. That could be some like old British junk. No data blocks would have been allocated, so the name resolver creates a directory entry and records the name to inode mapping. These steps do not actually go to the device. They're in memory. Your program writes API. Name resolver passes memory buffer to the storage allocation module, along with the inode. Storage allocation module allocates data blocks from the free list commensurate with the size of the file write. Creates a request for the disk write and hands the request to the device driver. Device driver adds a request to its request queue in concert with the disk scheduling algorithm, so it completes the write. Once the file write is completed, the device driver gets an interrupt from the disk controller that it's passed back up to the file system. Tells the CPU scheduler to continue the execution of your program. As far as the OS is confirmed, it's complete as soon as a request is handed. Interaction with the various subsystems. So let's review some software subsystems. CPU, virtual memory, file system, device drivers. Yeah, they're working together. Virtual memory manager services page faults. Implicitly performs I/O on behalf of the faulting process. File system explicitly performs I/O catering to the request of the user program to read and write files. In both cases, some mass storage device is the target of the I/O operation. The device driver pertinent to the specific I/O request performs the I/O request and reports the result of the I/O operation back to the requester. The device driver has to figure out somehow whose I/O request was completed upon I/O completion interrupt from the device driver controller. So you can use the program control block data structure that we introduced in Chapter 6 as a common vehicle among the subsystems. Okay, I don't really see what the second one was, or how it ever connected between them. But okay. So how does it take control of the resources and power up? So you have your OS image. Mass storage device is a disk. Master boot record. It's just a program. BIOS is a loader loading the program into memory, transferring control to the master boot record. MBR program knows the layout of the rest of the disk and knows the exact location of the operating system image. You might have multiple partitions. Single disk, dual boot. Partitions. So you have all these partitions, you have a partition table, and you have your MBR. MBR uses the partition table to determine which partition has to be activated depending on your user choice executed at boot time. There may be no choice if you have a single partition. So yeah, this makes sense. Used to be a dual booter back in the day. Depending on the OS to be booted up, the master boot register, master boot record, dang. Now, if you can store that in one register, I guess you'd have an infinitely sized register if you wanted to. There may be logical drives for. So these are partitions that have distinct file systems, logically distinct file systems. Shows the layout of the information in each partition. Other than the very first entry, the boot block varies from file system to file system. Let's assume this layout. You have a root of the file system, data, boot block, super block, storage management, data structures per file information. So let's look at each part of this. The boot block is the very first item. The master boot record reads the boot block if you're activating the partition. It's a program that loads the operating system. So every partition has a boot block, even if there's no OS. Super block contains all the information pertinent to the file system. So the boot program reads in the super block, contains a code, the magic number that identifies the type of the file system, the number of disk blocks, and other administrative information. Then you have the data structures. So it'll have like the bitmap free list. Could be the FAT if it is a FAT. Next entry, per file information maintained by the system. So this is like your inodes. Modern day file systems are all hierarchical. So you'll have the root directory. And the last one, disk blocks as containers for data and directory files. These are allocators. In-memory data structures. Talking about B trees. So a file system would read in the critical data structures from the disk into memory. File system does not even write to them immediately. Procrastination. First, many files, especially in a program development environment, have a short lifetime. Intermediate files, yeah, that's a good point. You delete them upon creation, so waiting while a file to write is advantageous since you can reduce I/O traffic. File system may batch the I/O request to reduce both the overhead and so it reduces, yeah, that's reduces like the time to the needle moves if you're using the look algorithm, and it decreases the amount of interrupts because you can just service them in batches. Interesting. There's a downside, and that's that the in-memory data structures may be out of sync. It is not safe to remove the device. Sync forces, right? System crashes. Must be fault tolerant. The operating system would dump the contents of the memory onto the mass storage device at a well-known location before terminating. And it'll load the crash image. It'll try to reconstruct the data structures. So it runs a file system check. If it doesn't, fails boot. CD is simpler. But you can't erase anything? I don't care about DVDs. I'm curious about SSDs. Random access, seek time to disk box. That's also a concern. Simplify allocation. Finite mini writes. Where leveling. Summary of modern file systems. Awesome. This is going to be nice. A lot of this is providing context for the Linux kernel development book. When I read operating systems 3 easy pieces, then the Linux kernel development book should be like quite easy. And it would be more of the exercise is just going through the source, honestly. Типа. So yeah. So let's read Linux. It's not changed. Internally it has, though. Multiple partitions, longer file names, larger files. Media versus network similarity. So now we have a virtual file system. Everything virtualized. Okay. So mission on Minix was the starting point for Linux. Started with Minix, it was replaced by Ext. Had several inefficiencies, giving rise to X2. It's not remarkably different from the generic description. You have a directory file, contents of an inode, integral number of continuous disk blocks. Each entry names a file or another subdir. You got an inode, len, type, len name, padding. My file name is long. Me too, huh? Wait out contiguously in the textual order of creation. So it becomes a previous one's padding. So it uses the hybrid allocation scheme. 12 data block addresses. First 12 blocks can be directly reached from the inode. Tries to allocate them contiguously. You have a single indirect pointer. So you have a points to a disk block that serves as a container for pointers to disk blocks. Okay. Okay. That's kind of smart. So you have one level of indirection pointer to a one-dimensional table. That gives you 128 more. Then you have a double one that gives you 2 to the 14 more. Then you have a triple one which gives you a ton more. Okay. So more storage slower, less storage faster, and you can kind of scale up to them. Journaling file systems. You think of writing to a file as writing to the data block. File size too small. iOS is buffer files. Write to disk opportunistically. Small files have a lot of internal fragmentation and a lot of time overhead. Got system crashes. That's kind of aged. To address the problem of inefficiency of writing to small files and aid in recovery, system crashes a journaling approach. Keeping a personal journey. One's personal diary is a time-ordered record of events. Instead of writing to the file, a log record that would contain the information corresponding to the file. Metadata modifications to the IO node and super block, as well as modifications to the data blocks. It's a time-ordered record. The journal is distinct from the file system, allows the operating system to optimize its implementation to best serve the file system needs. So it can be made more sequential. That's kind of smart. I was reading a little bit about something similar to this in the data-intensive application. General data structure. So you have all these logs. So as soon as the log is filled, then you write it. Aggregate small writes into bigger ones. Overcomes the small write problem, and it also helps crashes. So you don't need to like chuck everything in memory on the way out because it's already there. X3. Oh, the main thing about X3 is journaling. So Microsoft. I don't care. I'm never gonna use Microsoft. That is curious, yeah. I hate the freaking backslash in Windows. Studied the file system, attributes associated with a file, allocation strategies, metadata, implementation details, interaction between subsystems, layout of the files, data structures, system crashes, physical medias. Modern file systems in 2008. API is unchanged, but the implementation varies quite often. So yeah, I finished this book. Let's freaking go, dude. I spent a lot of hours reading this book. 700 pages, like, that is a fat book, bro. Dang, like the very first parts of this. It's kind of insane. Talking about instruction sets. Dang, this class is the scope of this is insane. We haven't really talked about the LC, but this goes to like the basics of computer architecture. Like we're talking about the add instruction. Then we're talking about multi-threading in C and libraries. This book is good. I think it's like the content. It does well with the content. I think that I was like occasionally bothered by like some grammar mistake, which is just like really unnecessarily confusing. And honestly, I'm kind of confused how it's even possible considering like each one of these chapters saying it's had like dozens of revisions, perhaps on average like 15 revisions. But it's like I feel like you would catch these things if you read it once. So I don't really know what to say there. But some of those are kind of annoying. Also, like I'm not a big fan of like everything needs an analogy. Like everything is either like a post office or like a baking shop or like just some like random junk. Like I'd rather just like I don't know. I feel like sometimes you can kind of cop out of having like a good explanation by just like saying, "Oh, this is good as an analogy," whereas like the best explanation for like a given thing is just like something that explains what it is in like understandable terms. Though that is quite subjective, so perhaps like I'm not even certain that if there weren't the analogies, that I would say like maybe I would say like, oh, I didn't really understand some things because there weren't analogies, so I could just be dumb. But yeah, the content, just the breadth of this book is insane. Like if you reading this book, you can have like you know how computers work if you read this book. And I will say like taking this class, like this is associated with a class. This has been one of the classes where I learned. Sorry, I just realized like I was watching one of my things yesterday. I was like, why am I saying like so much? And I just caught myself doing it again. And even like when I was doing yeah, the last time I presented as well, I said like way too many times. Like I remember bullying people for doing that like 10 years ago, bro. And now I'm doing that. Come on, bro. Not actually, but what was I saying? Oh yeah, like this class is probably. Oh my god, I just said it again. This class is one where I've learned the most out of like anything here. Dude, why do I keep saying it? Oh my god. It's actually really cringe. Bro has no self-control. So thinking on like first year, took data structures and algorithms, very elementary computing classes, object-oriented programming, class is garbage. Dang, our computing curriculum is actually kind of trash. Like unless you're sysarc, dude, why did it say like again? Unless you're sysarc, you don't actually learn anything about computers. Because how can you know, like, how can you graduate with a computer science degree and not know anything about assembly language? That's insane. Like, we're like a good. Dude, why do I do this? Where does this come from, dude? So cringe. Dude, this is so cringe. No. Every time I say like, okay, here we go. Every time I say like, I'm donating 5 cents. So let's get a calc. Every time I say like, besides like, so there's 0, let's do +1, you press equals every time. Every time I say like, that's like a filler. I'm donating 5 cents to open source. Let's do 10 cents. Okay. I just stopped talking entirely. That's good. So, what I was saying. GTCS curriculum is kind of trash, in my opinion. You're incentivized to take, well, this is also a fallacy of like, this is also part of why caring about GPA is dumb. Because if what you're trying to do is get a job working likely in, I said likely, that's an adverb. Like that's fine. Or working likely in web dev, honestly. And I consider like app mobile dev to be web dev. Your best strategy is to be good at LeetCode, have a good GPA, have some interesting projects. Projects that are interesting, particular to people that are like, particularly to people that are recruiters or not particularly. What am I trying to say? People looking at your resume don't know that a React to do app is trash. Or that any like, dude, this is ridiculous. Or that any I'm actually dumb, bro. What I'm saying is that to someone looking at your resume that's not a programmer, writing like a compiler or something, doing something that's like tough, that requires like, dude, oh my God. That requires lots of systems knowledge. That's hard to do. That ChatGPT won't give you in 10 seconds. People don't know that that's what that involves relative to following some React tutorial and making a website that looks nice and that people go on and use. And so you're incentivized like, this is actually embarrassing. I gotta like, wow. I am going to try this again. Wait, I don't think I'm gonna be out of money, bro. So, but yeah, it's not obvious to people that aren't programmers, and even some people that are uh, perhaps software engineers, of like of the relative difficulty of certain projects. And so there's not a point just from like okay, we're gonna try this again. As a CS student here, you're not incentivized to learn about computers. You're not incentivized to learn computer science nor computer engineering as a computer science major. If you want a job, your best tactic is to have a good GPA, know people, have good projects. Those three. Having a good GPA will, so for context, like most people are going to be working in like like in web, working on mobile apps, web backends, front ends, infra for web applications. And so these tasks are pretty menial. They don't require, at least at an entry level, knowledge of almost anything besides whatever framework you're using at a given time and just basic programming concepts. And so why would you choose to study something that's harder with lower average GPAs, with classes that take upwards of literally 10x as much time as classes in other concentrations? For instance, when I was media people, I took computer audio. I'm adding one for saying there. I took computer audio. The class is free and it teaches you nothing. You're writing audio plugins in Java with processing. This tech stack is unheard of in actually writing audio plugins. Everybody's just using C++ and JUice. That's a hyperbole, but yeah. So the classes are easier. They give you more time to work on projects. They keep your GPA 4.0 because these classes are free. But as a result, you don't know anything about computers. And so that's what I was saying when I said I feel like that's an intentional usage. This is one of the first classes where I learned something. Because these other classes, computer audio, computer ethics, not even to mention all this random junk I'm taking, like biology, where I'm just like staying up all night, getting behind on other projects, and not contributing to open source because I have to read about plant sex. So I'm just trying to think, as a first year, what did I learn? First semester I took freshman seminar, nothing. Physics 1, nothing. Linear, I learned a bit. I'm going to be taking second linear algebra. So I'll say I learned from linear algebra. I took... I'm gonna pull up my thing. I'm gonna go to the IP screen. Go to degree audit, caltech. So as the first year I took, oh, I also took a Spanish class. Nothing. I'm not gonna go by year, I'm just gonna go by class. APPH, or nothing. 1101 and 1102, high school. Calc 1, high school. Intro to computing, high school. That's like... That was easy. That was like... That was easy. That was on the basics of programming in Python. What is branching? What is looping? What are variables type? Quite free. I took 2 Russian classes. I learned something, but nothing on computer science. Physics, learned nothing. I should have just got a 5 on that. High school. Biology class I took in high school. Calc 2, high school. Linear algebra, I already said I learned something there. All of my history stuff. If you're coming in as an international student and you have to take this, that's actually just straight up insult. Lab science. So Chem, I took high school. I'm not doing another Chem class. So this is where I'm going into CS. Freshman Leap seminar, learned nothing. Discrete math, learned something, I'll call that useful. Object-oriented programming, learned nothing. Data structures and algorithms, I learned something, but I still think I could have learned that better on my own. I mean, same with everything on this list. Multivariable calculus, nothing. Objects and design, nothing. Computing in society, nothing. VIP, that's effective. VIP is literally just me working on an open source project that has to do with audio. I'd rather just be working on other open source projects. So the only thing I've learned in VIP is for myself, so nothing. 2110, I'll learn something. Systems and networks, learned a lot. Operating systems next semester. Probably learn more from reading the operating systems books, and that's the thing. Design an operating system is just a 30-hour weekly exercise in debugging C. Like, process to design, I imagine I'll learn a lot. Design and analysis of algorithms, I learned. That was useful. So let me just count. Useful, so we have discrete, just discrete right now. We have discrete, 2110, 2200. Design and analysis of algorithms. Compa. So I've taken 5 classes that were useful in 5 semesters. Wow. That's impressive, actually. And in the next semesters, I will take more useful classes because it's actually getting into stuff I volunteered to take. Linear algebra, compilers, advanced OS, advanced ALGS, automata, process design, OS. But these are classes you don't even take if you're not SysArc in theory. So if you're median people, you're actually learning approximately nothing. But I don't blame you for wanting to learn nothing, because you'll likely have better outcomes. Everyone works in web, approximately. So there's not really a reason to learn more. We could spend more time having a life and working on web projects. But yeah, I'm going to update my website. cdrecording.git, and them into here. This is going to be in the book list. So let's actually just update this in general. So this is done. Retro competing with class is out of here. Logical foundations up. Uber down. Linux kernel development down. I'm also reading advanced. Why is my OS crashing, bro? Advanced Verilog book. Advanced digital design with the Verilog hardware description language. I'm using NeoVim because it's fast. Why is it slow? Michael Setti? Right? Siletti. Is that right? Is there any other book I'm missing? I don't think so. Alright. So that's that. Finished that book. Awesome. So what did I say I was going to do next? DSA? Oh yeah, let's get on LeetCode. LeetCode. While I'm logging in, let me go to IP. IP. Okay. I think I actually bought premium. Like I bought a year premium. And used it for like 5 minutes. It's kind of dope. What's my username? I have like 40 accounts on here. This is a Twitch. See what they're asking these days. So we're gonna do these 6 questions. Designing a file system. So these are some easies and mediums. So we're gonna be doing these questions. Alright, so I'm gonna try to desaw some meat. Right, go to the onion and do some of this, get some water. Okay. this first question and then cook. I think that's a move. So it's my office hours over. It's about to. All right. I share my YouTube account, by the way. So don't rage at me if there's something crazy in the search results. Sequel. Huh? No, you got me tripping, bro. I'm not doing that. It's gonna be a programming exercise. Dude, I should learn Erlang. How do they have Erlang on here? That's so random. No Haskell, but you have Erlang? Alright. You have some coins. The ith coin has a probability of prob of facing heads when tossed. And the probability. Number of coins facing head equals target if you flip each coin exactly once. So these are the probabilities. So we have some coins. The ith coin is a probability of prob facing heads. So return the probability that the number of coins facing heads equals target if you toss each coin exactly once. So we have an array of floats, and we're trying to show probability. So they represent probabilities. So in this case, you're just multiplying. Do you not just multiply them? Do you not just multiply them? That's the target. Returning the probability that the number of coins facing heads equals the target. So in this case, so the problem is when you have differing probabilities. So imagine the case 0.5. Let's imagine the case 0 and 1. With a t with a target of 1. Let's instead do like, yeah, let's do like 0.1 and 0.9. Probability that, so so we're looking at 1. Probability that one of these is heads is 0.1 plus 0.5 plus 0.9. Probability that 3 of them are heads, 0.1 times 0.5 times 0.9. Probability that 2 of them are heads. So how many ways are there for there to be 2 that are heads? You have AB, BC, and AC. So the probability that 2 of them are heads are these 2 times the inverse of this one plus these 2 plus the inverse of that one plus these 2 times the inverse of that. So this is like a math question. So the situation. I'm trying to think of a way that's not brute force. So I'm gonna look at the first hint. Dynamic programming. Okay, so let's consider a dynamic programming approach. The problem is the target. Number of coins facing heads equals target. Yeah, so I know you could like, oh, what's the probability that this one? But how does the target work? Let's look at the second one. Use DP with 2 states. Pause and count. Pause coin. The position the coin and count as number of heads seen so far. I might not understand this question, bro. How do you deal with a target? Because it could be that you have to consider every possible combination with target heads. Generating functions. Yeah, I don't know anything about that. Yeah, I think I need a video on this one. YouTube, lead code, 30.
Hey, everybody, this is Larry. This is me doing the weekly premium problem on June. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think.
YouTube's video
I'm here back in
thing is
Barcelona
trash.
in Armenia. Hope
Just
everybody's
bricked
doing
my
well.
whole browser. When I clicked full screen, it didn't.
That was a premium problem, so which is actually kind of weird. But let's see what this problem is about. Because I didn't. What is this? 2019. Was it not a premium problem before or something? That's kind of weird. Anyway, so you have some coins, and also 2019. Wow, 4 years ago. Yikes. Man, time flies, doesn't it? 4 years of videos. Anyway, okay. Dive coin as private buy or facing heads when tossed. Okay, so return the number of heads facing heads you go target if you toss every coin exactly once. I mean, this is just going to be a binomial, right? Yeah, so basically, okay. Yeah, this is kind of tricky if you haven't done it before, but basically the idea is that it is dynamic programming, it is probability theory, and yeah, and we can write it out but we can also just like reason it out one by one. We could look at the coins one by one and then just do the math on how it changes the answer, right? And here we can maybe do something like, I don't know, I call it calculate because I'm lazy, or like that's the hard part is naming it. And then left, right, meaning number of heads left. And basically, if left is less than 0, we return 0.0 because that means that we went over the target, right? If left is, okay, so otherwise, n is equal to, say, length of probability, right? And otherwise, if index is equal to n, then if left is equal to 0, we return 1.0, otherwise we return 0.0, right? Otherwise, then we just keep doing it. We calculate index plus 1. So basically now, given probability of index, we have two things we can do, right? We can probability index of index times this, and this is going to be left minus 1 because we used that, we got ahead, right? And then, so this is P getting head, right? And then P get tail is
You know when P's getting head, bro.
here, but 1 minus probability of index times calculate index plus 1 left unchanged. And then yeah. I mean, I think this is right, but it is kind of, maybe the phrasing is a little bit, because, yeah. But yeah, so that's pretty much the idea. And then we return, calculate, 0, target. And of course, we have to do memorization, but this will give us a start. And of course, maybe we want something, just a little bit funky. And keeping in mind that in this particular example, the order doesn't actually even matter, right? So in case you wanted to, I don't know. But this may start, to be exponential, so this is why we need to add memorization, right? And here you can easily see that, it ran, but index goes from 0 to n, left goes from 0 to target, and target is less than n, or less than equal to, I guess. So this is going to be n square input. Each of these do O of 1 time, so we can easily cache. So yeah. And then after that, the caching retrieval, right? So if as cache, index left, return cache of index left. Otherwise, yeah. And that's pretty much it. Just memorization. Then you can see that improved the time significantly, and then we could give it a submit, and hopefully I didn't make a silly mistake somewhere. And there you go. This is going to be n squared time, n squared space, and yeah, if you do get this one, try writing it as bottoms up as a challenge, and then after that, you can realize that you can actually do a space optimization trick on this problem to get space to linear space as well. So definitely check that out. I'm tired, my shoulder hurts, everything hurts, so I'm gonna go today. So stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye.
Like I saw him write it, I don't really understand it though. I don't understand how you can, why you don't have to look at every possible target. Every possible set of the ones that are heads of like target. No comments. See if there's a solution. Or there's an editorial here. Toss each coin one by one and generate all possible combinations of coin tosses and add the probability where we get target number of heads. Yeah, I understand like the add or multiply. Want to find the probability of two independent events occurring together. You multiply. Want to find the probability of either of two mutually exclusive events occurring. You need to add the probabilities. Consider the first coin in the case where it shows a head. You need target minus one heads from the remaining coins. You can consider the probability of this as the probability of the first coin facing heads multiplied by the probability of getting target minus one heads from the remaining coins. Now for the tails. You need target heads from the remaining coins. 1 minus the probability of facing head multiplied by the probability of getting target heads. I agree, you add them to get the probability of both heads. So in this recursion, you need to consider the index of the coin under consideration and the number of more heads required. So you're finding the probability that index plus 1 with target minus 1 times the probability of the index. Okay? So you add the probability that this one's heads and the next ones are target minus 1, and you with the probability that this one's tails and the next ones are target. Where find probability is a recursive method that returns a probability of getting target heads using coins index from. Because we're decrementing target by 1. So there are some subproblems here. Use minimization. Bro, this is a medium? I'm cooked, bro. As you know, the current state of the subproblem depends on the start index of the remaining array and the target heads we need to get there in the remaining array. You can use a 2D array. But this is actually super hard. Let's try it. So I know we're doing find prob. Uh, dot size. Understand we're starting at 0 target. And that's what we return. Can you even listen? Rob. What does this take in? This takes in on the left. This doesn't need to be another 2. So what are we doing here? So if the target is equal to 0, perhaps a less than 0, or 0.0 because it won't reach target. If target is left is greater than left. Still confused, bro. Index, target, and end. They're saying if the target is less than 0, too many heads. Turn 0 to 0. If index is equal to n, index is n, index is the length probability. That means we're at the very right. Now if target is 0, so if you need 0 more, probability is 1. Otherwise, if you need more, the probability is 0. Okay. So you need the memo. The length. And redoing this memo. Why return? People that use mouse and arrow keys are crazy. So we're doing. So the function is memo of index target is equal to find prob. So we're going to be multiplying two things here. We're going to be adding the probability of this times prob of index plus find prob something else times prob index and 1 minus. Alright, so this is index plus 1, and then target minus 1. This is index plus 1 and target. And you just return that. Well, doesn't look like it ever returns. Dang, my thing is breaking the whole site. I think we just gotta pass it in. Can't capture that either. Venom. N is equal to target is U size. Got a vac. Memo 0. For all the probabilities, V is equal to the probability of heads, so AV is equal to the probability of tails. New memo. N plus 1. Memo of 0. Memo 0 times AV. Give me a good explanation on this. You're setting a memo list. You're multiplying the 0th element by the property that is instead tails. For J until target. Multiply them by something else. Probability of having 0 heads after the current coin is the probability of having 0 heads before. I would not think this is true. The probability of having 0 heads after the current coin is the probability of having 0 heads before. The current coin landing on tails. Huh? So this stores the probability of getting 0 heads. Target. Do you flip target times? Same as the probability of getting 0 heads after you flip target times. Assuming the probability of having 0 heads. I moved here, but that's probably 0 heads before tossing the coin. None of the previous coins have landed heads. To maintain 0 heads after tossing the current coin must land tails. The only way to have 0 heads after tossing the current coin. Oh. Yeah, that's obvious. I thought I meant 0 heads. Yeah, okay. Yeah, that makes sense. But what does that have to do with the question? What exactly is a memo? The probabilities of what? The probabilities. Memo is initialized with zeros except for memo of 0. The base case. So what is in it? So understand the base case is the probability of having 0 heads. It reflects the probabilities of achieving different numbers of heads as each new coin is considered. So these are like the numbers of heads you can add, and the value there is the probability of the current coin that we got that many heads. So before tossing any coins, you have 0 heads, and the probability is 1.0. The max amount of heads we can get. So the length. Okay. So it's looking at it from, we have an array. The indices are the amount of heads at the current coin is the probability. So it'll sum up to 1. For each coin, you update memo to account for the new probabilities introduced by this coin. So this coin can either be heads or tails. So if it's tails, the number of heads doesn't change. So the new memo is equal to memo plus, why is it plus equals? Okay, so that makes sense. So for all the rolls, so that makes sense. For all the woes would do this. And then we're returning the probability that we got this many heads. Probability of all of them being heads. Target of there being target heads after you roll all the coins. So what is it? So it's what? Huge new. Let's go to the same back. So we're making the same back. And for all the entries in the back, putting in new memo of J. So you go to memo J minus 1 times V. Ooh. Times prob at I plus memo of J 1 minus the prob at I. Memo, so get a new memo. Wow. So on the ith roll, we just keep rolling all these dice. Or keep flipping all these coins. The new memo. So we're updating memo. For all the elements from 1 to n. Integer, so let's subtract f64 from integer. One minus prob of I. What's the difference? Target is usize of x 0.0 to n plus 1, 1.0, 0 to prob 1, new mutable memo 0.0 to n plus 1, for j 1 to n, new memo of j is equal to j minus 1 times prob of I plus memo times minus prob of I. Do you have to pull them out? Why would that matter? Why would you have to pull them out? Not that. What is the difference, bro? Turning memo of n. Memo is equal to new memo. Oh wait. I missed that the 0th element you have to multiply by the probability of getting tails. Yeah. Probability of getting 0 heads is probability of getting all tails. New memo 0 is equal to memo 0 times 1 minus 1.0 minus prob I. So you memorize all of the probabilities. So at a given step, you memorize the amount of Memorize the amount of times that you memorize the probability. So these represent all the different targets, all the different amounts of heads we've got. You memorize the probability that you achieve this many heads. So at each step, you update the probability of each one being heads by saying the probability that it's heads after this roll is the probability that it was before times the probability of rolling tails plus the probability of it being one head less than it was before plus the probability of rolling heads. Okay. That's kind of a goated solution. So that felt like it took a long time. It's probably after my office hours. I think that already took an hour. That's crazy. So we can leave this. How long did that take? I'm curious. Yeah, that actually took an hour. Wow. And that's a medium? If that's a medium, it might be over. Gonna look at the solution to this before I. This is like an object-oriented design question. Yeah, I can do this. All right. So. So I'm going to make some lunch, do the OA, and then come back for a later one. So that was a solid little 2.5 hour stream. Finished that book. I did a single week code problem that took an hour. Well, all right. See ya.